welcome. So in the last class we have been discussing about Monte Carlo and molecular dynamics simulations, and I ended up saying about the thermodynamics. I would say some review of thermodynamic concepts that we discussed in the context of simulations. So today I will build up on that further to discuss what is known as a solution thermodynamics, and based on that we will develop the thermodynamics of polymer solutions. So just to put this in context, what we have discussed earlier in the very beginning were like the models of a random walk that we applied to a single polymer chain. After this we have discussed different cases where we have some interaction between segments, like good solvent or poor solvent cases, but again we were looking at a single polymer chain. So now I want to take a slightly zoomed out view and look at the behavior of a solution, and by behavior I really mean a macroscopic behavior to begin with, and then we will come back to a microscopic model for that behavior of polymer solutions. But let us say we are zooming out and we do not look at a polymer chain, we look at the solution of polymer chains that is contained in there. So it is very microscopic or macroscopic compared to the view that we had earlier. Okay, but before that let me just recap some idea of thermodynamics of simple solutions that does not contain polymer, right. So let us think about a liquid solution and for the sake of simplicity let us say there are only two components which we call solute and solvent. These are my two components and it is a single phase liquid to begin with. Okay, we will come back to the idea about phases in a moment, but let us say it is single phase liquid to begin with. Then in that case, if I use the Gibbs phase rule, it tells me the number of intensive variables I need to specify in order to get the thermodynamic behavior of the system. Number of intensive variable required to specify thermodynamic behavior of system, and in this case C is the number of components which is 2, P is the number of phases which is 1, so we get 3. So we can have 3 intensive variables which will perfectly characterize the system. Now we can make various choices, again keeping in mind the idea that we discussed regarding the conjugate variables. So let us say I pick temperature, pressure and composition. So composition I can specify in two ways. I can say either in terms of number of solute and number of solvent, so where I refer solute as P and solvent as S. But now if I say in terms of number of molecules, then these two are not intensive, they are of course extensive variables. If I want to use an intensive variable, we can just define a mole fraction or a volume fraction that will be intensive. So this will be like extensive and this will be intensive. So, we can either specify Tpx or we can specify Tp, Np, Ns, because using Np and Ns I can find x. Okay. Essentially you only need 3 intensive variables. So, if I am given both Np and Ns, that is the number of molecules of solute and solvent, I can get the x, that is the mole fraction. So, now the relevant energy function in this case is the Gibbs free energy, which I can write in terms of Helmholtz free energy, and for the reasons we will discuss in a moment. So, the Gibbs free energy can be written like A plus PV, where A here is a function of Np, Ns, T and V plus PV. Okay. So, now we will note here that although we started with a Gibbs free energy, which was a function of temperature, pressure and composition, if I write in terms of the temperature, volume and composition, that is if I use the Helmholtz free energy, of course I can separate out the PV term, but it gives me certain mathematical convenience when I am doing this, and I will elaborate on that in this lecture. So, before this, if I want to define the volume fraction of solute, I can define E as something like the following, where Vp and Vs are specific volumes of solute and solvent molecules So, keep in mind that we do not refer to the actual volume of molecules, because exactly what does volume mean anyway. So, let us say if we have water, how do we define its volume? Is it the volume of electron cloud? Is it some sort of a volume occupied by the molecule? It is very arbitrary concept. So, the way we are defining a specific volume is the change in the volume if I add a molecule of water to a certain volume that is present already. So, it is defined as a change in volume, not as a volume of the molecule itself. It makes some difference in the actual meaning. What it means is that it can be dependent on the composition. The change in volume may be different by adding one molecule. If I add in say a solvent that is favorable to that molecule, or a solvent that is not favorable. We will come back to this later, but the basic idea is that we define Vp as dou V by dou Np, the change in volume. If I keep the temperature, pressure and number of solvent molecules fixed, if I add a molecule of solute. So, it can be different in dilute solution compared to a concentrated solution, because change in volume may in turn depend on the interactions present inside the system. Okay. Similarly, I can define Vs as the following. So, with this particular definitions of specific volumes, we can talk in terms of volume fraction of solute. Of course, for solvent it has to be 1 minus phi, because both of them must add to 1, because there is no void. It is either containing a solute or containing a solvent. So, now although I have just said, then Vp and Vs can be not constant, it can differ with the concentration and so on. We will now assume that, let us what happens when they are constant. This is an assumption. Until so far what we are doing is somewhat rigorous. Now what we are making is an assumption. So, we assume that Vp and Vs are constant. So, now by the way, before I do this, I can write my volume V as Vp Np plus Vs Ns, and this is also quite general. It is before the assumption that I am just making. So, if the Vp and Vs are constant, then for a constant value of Np and Ns, the volume is also constant. Okay? Because if Vp and Vs are constant here, Np Ns is anyway constant. So, V will be constant. What this means is the solution is what is known as an incompressible solution, because there is no pressure here in the expression I am writing. Of course, the pressure may appear in the actual definition of specific volumes, but if I ignore that, then in that case what I am assuming is that the specific volumes are constant. That means volume is constant, and when the volume is constant, the system is considered incompressible. So, the pressure does not change the volume. So, although pressure and volume are conjugate variables and we should work in terms of either P or V, since we assume V to be constant, it does not matter, I can work in terms of both P and V. I can equivalently work in Helmholtz free energy as I can do in terms of Gibbs free energy, and that is the reason why we use the Helmholtz free energy, because it will be simpler for the analysis that we will do. So, now going back to where we started with, I wrote G as a function of this, which is PV plus A Ns and P Ns V T. V is anyway a constant here, so I can write it as so I gotten rid of one variable because volume is constant. So, now if I look at this particular A term, then A is also an extensive variable, because the energy will change if the quantity of matter will change. Energy is extensive. So, now what it means is, since A is extensive, I can write, if I take alpha times number of molecules of both solute and solvent, I should get an energy that is alpha times the case that we started with. Okay? Just a mathematical trick that will give you some dividends in a moment. So, now I can set alpha as, say, Vp by V. So, then I will have A Np Vp by V Now, let us recall from here, then this term is same as phi, because denominator is capital V here. So, we have a phi appearing here. This term, if you notice carefully, is, I am sorry, there was no alpha here. If you notice carefully, I can write it as Vp by Vs multiplied by Ns Vs by V. Now, this term inside the bracket is 1 minus of phi. So, we have Vp by Vs 1 minus of phi. Now, you note down like what do you have on the left hand side. So, the first two terms I have represented as a function of phi and temperature, because Vp by Vs is anyway a constant. So, this term is anyway a constant. So, I can write it as a function of phi and temperature. So, we have reduced one more variable. We no longer talk about the number of molecules of solute and solvent. I talk about the volume fraction of solute. And then what I can write is A of NP-NST is equal to volume times some function of phi t, where basically I consume the factor Vp by dividing by A and call that thing F. The basic idea is I am writing the Helmholtz free energy in terms of something we can refer to as a Helmholtz free energy density. So, phi F of phi t we will refer as Helmholtz free energy density. That simply means that if I multiply it by volume, I will get the Helmholtz free energy. So, going back here, my G is now P V plus V multiplied by F of phi t, which means okay. So, now I have a simple expression of the Gibbs free energy of the system in terms of a PV term and something that we refer to as the Helmholtz free energy density. We do not know what is the functional form of that f of phi t yet, but we can I will show you that why is that particular form is very convenient to look at the mixing behavior and the phase separation behavior of the systems. Before this, let us define what do I mean by mixing and phase separation. So, let us say if I start with two volumes of containers containing different volumes and different amounts of the solute. Let us say the first one has a volume V1, the other one has a volume V2, and they have volume fractions of solute phi1 and phi2. If I add them together, we may form a new volume V with a net volume fraction phi. This will only happen if the system has a tendency to mix. On the other hand, if somehow even if I manage to mix a system to have a certain volume fraction phi and volume V, but the system does not have a tendency to remain homogeneous or remain in the mixed state, it will phase separate to Okay. Essentially, we always draw it within the same beaker just to demonstrate that they are the different layers of volume that you can have. So, one of them you can call a concentrate, other one you can call it a dilute phase. There are other things. Basically, we can talk in terms of equality of chemical potential in the two phases when we discuss the phase separation. The basic idea that I want to point out here is the system phase separates to two phases. So, now the question is, how does the function that we have derived, the Gibbs free energy, that was in terms of a Helmholtz free energy density f of phi t. So, how does this function f of phi t can characterize the mixing and phase behavior? What should be the form of that function that will give you a mixing behavior in systems? What will be the form that will give you a phase separation behavior? First of all, before this, we want to know whether that function is sufficient to characterize the mixing and phase separation behavior or not. We will see like when will this mixing or phase separation will occur, what is the criteria for that to happen. So, if for example, we look at the first situation, the Helmholtz energy of the system is V1 F phi1, and if I say the pressure is P, then we have P V1 plus V1 phi1 as the Gibbs free energy, let us call it G1. Then similarly for the second liquid, we have V2P plus V2 F of phi2, and if they come together and form a homogeneous phase, we have G3 is equal to V of P plus V of F of phi. We are assuming that it is happening at a constant temperature, such that we can write f of phi t as simply f of phi. So, now we know from thermodynamics that the process will be favored if the resulting Gibbs free energy will be less than the sum of the Gibbs free energy of the phases that I have mixed together. That means Vp plus Vf phi must be less than V1p plus V1f phi1 plus V2p plus V2f phi1 phi2. The first thing to note here is, since the volumes are assumed to be constant, when I add them together, V1 plus V2 become equal to V. That means a specific volume is assumed to be constant. So, what this means is I can really cancel out these three terms, and what I am left with is basically a term containing only the Helmholtz free energy density So, the mixing will happen if this is the case, or if I divide by V, I can say mixing will happen if we have where x1 is equal to V1 by V. So, for mixing, similar idea we can apply to phase separation. So, for phase separation, we should have V of f phi. Now, the final state is phase separated, which has two phases. The energy in that state should be lesser than the energy in the homogeneous state. So, this should be higher than, so I called it as A, or I can say there is small detail here or an error earlier. The volume of the two phases has to be different, it must be V A and V B. So, now we have where x A is equal to V A by V. Okay. So, now we have a simple mathematical relation in terms of the function phi that characterizes the mixing and separation behavior. We have not yet discussed what the mathematical form is, but we have already discussed what the mathematical form should be to have certain type of behavior that we can see. So, the next class I will elaborate on this in more detail. Then I will discuss that the other ideas that we discuss in thermodynamics like osmotic potential and osmotic pressure and chemical potential, they can also be written in terms of this function f of phi for liquid solutions. And then finally, we can extend the idea to polymer solutions and try to find what that function f is, and based on that we can talk about the mixing and phase behavior in polymer solutions and other polymeric systems. Thank you.